To begin, you should know the characteristics of the states of matter. 3 states of matter: solid, liquid, gas. And first 4 characteristics: shape, volume, density, compressibility. Shapes in solids, fixed. Shapes in liquid takes the shape of the container and the surface would be horizontal. Shape in gas, the gas takes up the entire shape of whatever container it is in. Volume is kind of similar. The volume is fixed, but for liquid, the volume is also fixed. Slight expansions based on temperature in both solid and liquid. And in gas, the volume would vary, so it will always expand to fill the container. So that's the key difference there for volume. Density: solids are usually the most dense, liquids in the middle, and gases are very not dense, the least dense. Compressibility: we basically can't compress solids under normal conditions. Very hard to compress, very difficult to compress. Liquids have a little more compressibility in them, can experience some compression under high pressure. And gases are very easy to compress. You can compress gases with your own strength. So now we should know additional characteristics of solid, liquids, and gases, this time looking at it from a particular particle point of view. Forces of attraction between the particles in a solid: strong, weaker than solids. For liquids and for gases, it's very weak. The energy of the particles, relatively speaking, it's small for solids. It's more EK. This EK here stands for energy from kinetic energy. Kinetic energy in solids is less than in liquids. Liquids it's more, but in gases it's very large when you compare it to solids and liquids. Movement in solids, you just have that vibration about a fixed axis, fixed position. In liquids, there's no fixed position, but they still stay relatively close to each other, so they move slowly and closely past each other. And in gases, we have free, rapid movement. Now, these characteristics, you want to find a way to memorize them, and memorize them exactly like how I have them right here, right? The last thing that we look at for solids, liquids, and gases is how the particles are arranged. And for solids, we expect them to be packed closely together, and it's usually in an organized, regular way. Liquids is still pretty close together, but there's some more spaces as compared to a solid, and the arrangement is random. And in gases, of course, there's relatively large space between the particle, and it's a random arrangement. When a solid goes to a liquid, that's melting. When a liquid goes to a gas, that's boiling. But it can also be evaporation. Evaporation and boiling is changing the liquid to the gas, but there's a key difference with it. Do you know the difference? I'm going to talk about it just now. Backwards, going down from a gas to a liquid, what do you call that? You call that condensation. Liquid to a solid, what is that? Liquid to a solid, that's freezing. So as you go up, we add heat, and as we go down, you notice I put any blue? Blue for freezing, blue for removing heat. And is that evaporation can occur at any temperature. That's the key thing, and they ask this a lot in the exam. They like to ask this. So 2 things, it can take place at any temperature. Another key characteristic about this phenomenon called evaporation is that it occurs at the surface of the liquid. So only those molecules at the surface sometimes say, well, you know what, I want to be a gas, and they break free and they become a gas, right? Do you know 3 things that can increase the evaporation rate of a liquid? Write it in the chat below. And boiling, what's different with boiling? Boiling happens at a specific temperature for that substance. So it must happen at a specific temperature. The boiling point of pure water is 100 degrees Celsius. And it occurs throughout the liquid. So once the entire liquid is at 100 degrees Celsius, any one of those molecules could say it's time to become a gas and dive out. It's time to examine the rare situation. A rare situation can happen if a solid goes to a gas. That's called sublimation. And if a gas goes to a solid, that's actually called deposition. What is an example of this? The most popular example of this is carbon dioxide, aka dry ice. Maybe you have played with it before. It just turns straight from solid into gas. And another example is iodine. All right, so I have 2 axes here. What is this for? What is this for? So that would be a cooling curve. It's getting cooler. It's going down in temperature as the time increases. And if I do it the opposite way, that's what a heating curve. So what we can see here is different states: gas, liquid, and solid. The line that holds constant temperature, and physics students will know this, is we have two situations where that happen. When the gas turns to liquid, during that period the temperature will remain constant, and when the solid turns to liquid, during that period the temperature remains constant. We call it latent heat of vaporization, latent heat of freezing. Some other features about this graph is that we are taking the temperature at constant time intervals, and we expect the temperature to go down with a constant gradient. It's called a cooling curve, but a lot of the graph consists of straight lines, and we expect it to remain at this constant temperature at the boiling point. So using a cooling curve, you may have done this experiment in your school. We can determine the boiling point of a substance. We do it a lot with naphthalene and waxy substance like paraffin. Diffusion. Diffusion is the net movement of particles from a region of high concentration to a region of low concentration until they are evenly distributed. For diffusion to occur, the particles must be in a gas or liquid so they can diffuse. The syllabus were to know two examples. So let me get two examples. The two examples from the syllabus, right? Just take two cotton balls, dip it, one in concentrated hydrochloric acid, one in ammonia solution, put it on the edge of test tubes, and the hydrochloric acid solution gives off HCl gas, and the ammonia solution gives off ammonia gas, and the two of them, when they come together, they react to form NH4Cl, which is a solid. Kind of form a little cloud in the middle, right? So the only way that could happen is if the particles that was on the end minding their own business diffuse through the test tube. Example one. Make sure you know the formula. This come real plenty. Side note about this, the ammonia particles diffuse quickly and faster than the HCl gas. So the cloud normally forms closer to the HCl gas side, and that's something they could ask you about as well. Example number 2 is a very popular one. If you didn't duck chemistry class, for sure, if you didn't duck a lab, you do this already. That's potassium manganate 7, purple crystal, drop it in the water. It's get all over your school uniform. And as you drop it in the water, it diffuses through the Petri dish. I'll show you do this already. Press like on the video if you did it. So if you leave it inside the Petri dish for long enough, the whole thing will turn purple until everything is evenly distributed. Diffusion. Definition: osmosis. So osmosis is the movement of water molecules this time, not just particles like diffusion. Or it can be molecules of a solvent, but for CXC, water molecules, right? Through a selectively permeable membrane. Remember that term. And it's going from a region of high concentration of water molecules, which means a dilute solution, because it's a lot of water, so it dilute, to a region of low concentration of water molecules, which would mean a concentrated solution. Kind of reverse and trippy, right? So that's the definition. Memorize it. Once again, you need to come with your two examples for osmosis. Example number 1, this. So in this sac thing, it's a differential. I prefer the word selectively. It's a permeable membrane. So water molecules could go through, but the sucrose solution inside can't go through. So inside there is a really concentrated solution of sucrose. Because it's concentrated with sucrose, the ratio of water molecules to the sucrose molecules is low. So this has a low concentration of water molecules. So what will happen? The water want to go inside to dilute. So it will end up going through this selectively permeable membrane. And it actually raises the level that you would see on that little glass tube on top there. It goes up. That's a lab. Have you done that lab before? So the volume of the concentrated solution increases, and that causes a visible rise in the meniscus in the level of the test tube. That's osmosis happening there. Another example. If we cut strips of potato, which is concentrated with starch and them kind of thing, and we put it in a dilute solution, the potato gets soggy and it gets turgid, it gets filled with water because the water will enter into the potato. Osmosis. The water molecules going from a region of high concentration of water molecules to a region of low concentration of water molecules. But if we take the same potato strips and we put it in like really salty water, the water will be sucked out of the potato strips via osmosis, because inside the potato strips not that concentrated, so the water molecules will be like It are plenty of we here, but it are plenty of we there proportionally. So we will head out, and it actually lets the potato strips be more bendy. The potato strips will be shorter, softer. Osmosis. So all of this talk here is from just the first part in the syllabus and the very first point in the syllabus. And what they're really talking about is evidence to support the particulate theory of matter. So there are 4 points to the particulate theory of matter. Point 1, all matter is composed of particles. I hope you're memorizing this. The particles are in constant motion. This is affected by the temperature. Number 3, the particles have empty spaces between them. And number 4, the particles have forces of attraction between them. And some bonus points that you can mention. For a fixed system, there's conservation of mass. So it doesn't matter chemical, physical reactions, anything that occur in that fixed system, you'll have the same mass. The mass must remain constant. And any change in state is as a result of particle behavior. Remember the temperature make particle vibrate fast, and remember we was doing the solid liquid gases thing. Yeah, all of that lead from this. And that, in fact, it actually come after this in the syllabus. I wonder why I do it first. Back to the syllabus, if you look at this little part here, they can actually throw out a question on that. The use of salt or sugar to control garden pests or as a preservative. So what farmers could do is they put salt around their plants, so they can put salt on animals like, let's say, slugs that eating out the leaf. Remember the osmosis? It concentrated on the skin, so it will draw water out of the animal and it will actually dehydrate the animal. That's a rough way to go, but you're saving the plants. Same thing with why salt is used as a preservative. One, yes, it will dehydrate the food, but more importantly, it's an environment that bacteria will have a real hard time developing and growing in. Yeah, there's some kind of salt resistant bacteria because it will draw the water out of the bacteria and kill it. So it keeps food preserved for a long time. So back in the days, salt was a key part of preservative techniques, but now we have the fridge and thing. Let's take a dive into matter and let's study this flowchart. This is a whole series of memorization that you have to do for the exam involving matter, splitting it into 2 different categories: pure substances, mixtures. Pure substances splitting into 2 categories: element, compound. Mixtures splitting into 2 categories: homogeneous and heterogeneous. Homogeneous have that 1 category, solutions, and heterogeneous have the colloid and the suspension. And then solutions goes further on into the solubility curve, and all these go further on into separation techniques, colloid, suspension, separation techniques. So there's a whole bunch of memorization for this topic, and you just have to have it clean. Let me go. A pure substance composed of a single type of material only. For pure substances, we can highlight 2 general characteristics. 1, its composition and properties are fixed and constant. For example, the melting point, boiling point, density would be fixed. 2, the component parts cannot be separated by physical processes. And the caveat, if you want to find out if a substance is pure, you can melt it, and if it's pure, it will hold the melting point designated for that specific pure element or compound. So pure substances can be split into 2 categories: elements and compounds. An element is a pure substance that cannot be broken down into simpler substances by using an ordinary physical or chemical process. It's just, you have to go and do some kind of subatomic something to break this down, right? So it's just at an atomic level. In fact, an atom is an element, or you could have a diatomic molecule like O2, oxygen. And there are a whole bunch of elements found in this guy, periodic table, and there are lots of different trends and exceptions that we will have to study in that just now. But for now, the periodic table can be considered as non-metals and metals. So the other pure substance is a compound, and a compound is a pure substance that is formed from 2 or more different types of elements which are chemically bonded together in fixed proportions and in a way that their properties have changed. And the most popular example for a chem student is sodium chloride, which is formed from sodium and chlorine. So sodium and chlorine, you can't eat that. You can't consume sodium, you can't consume chlorine. They are bad boys in their own metal and non-metal category. But sodium chloride, humble guy, that is sprinkled on nearly every food. Salt, with a chemical formula of NaCl, and of course we're going to jump into chemical formulas soon. So let's go back to this flow chart and we're going to talk about mixtures. What is a mixture? So in a mixture, each component gets to retain its own individual properties and it is not chemically bonded to any other component in the mixture. It consists of two or more substances, pure substances like an element or a compound, which are physically combined together in varying proportions. And moving forward, we can categorize mixtures as either homogeneous or heterogeneous. You know how much kicks we used to get in school with them too. For some reason, school just say. So a mixture that is homogeneous is uniform. That's a nice word that you'll throw in there. It's a uniform mixture, and the composition and properties are the same throughout the mixture, even if you go down at a really small scale. This means we cannot distinguish each component in that type of mixture. And the classic example for that is a solution. All solutions are homogeneous. The heterogeneous mixture is a non-uniform, instead of uniform, non-uniform mixture. And it is possible to distinguish each component, sometimes even through your naked eye. And the two examples for that would be a colloid and a suspension. So they go in particle size, they increase in particle size like this. Solution, smallest possible particle size in the mixture. Colloid is in between, and suspension, largest particle size in terms of mixture. So all those are considered mixtures. The solution is a mixture, but in a solution, like an example is salt in water, the salt goes down to a really small, tiny, we cannot even see it with our own naked eye. You can't see the salt floating around in the water. It is evenly distributed. So a solution is a homogeneous mixture, two or more substances. One substance is usually a liquid, but that's not always the case. You could have all kinds of different types of solutions. The solvent is the substance that does the dissolving, and you have more of that. It's present in a higher concentration. The solute is the substance that is dissolved, full stop, that is dissolved. And you would have this in a lower concentration to the solvent. So the solute dissolves into the solvent. Special term, saturated solution. A saturated solution is a solution in which the solvent cannot dissolve any more solute at a particular temperature. And because of that whole temperature with saturated solution, we can create something called the solubility curve, which I'll talk about just now. What's some examples here? You could have like the solid being a solid and the liquid being the solvent. The most popular example of this is seawater, salt and water. Then you could have liquid and liquid. The most popular example of this in Trinidad is when people use water as a chaser with rum. That is liquid and liquid as a solution. If in the exam don't put that, you could probably put ethanol and water. Ethanol and water is hand sanitizer. A next type of solution, gas in liquid. Most popular example is, how you say it again? Sweet drink. Sweet drink. Carbon dioxide in the water, aka soda water. There are even solid solutions where after they are mixed, they form a solid and it's a solution. It's considered a solution. And the most popular example of that is bronze. Alloys, a metal alloy. Bronze, you have tin dissolved in copper. And we could even have gas solutions like air, mixture of nitrogen, dioxide, carbon dioxide, oxygen, all of these. So let's go up in particle size to a heterogeneous mixture. The first one, the colloid. And colloids are heterogeneous mixture in which minute particles of one substance are dispersed in another substance. It's usually a liquid. And the dispersed particles are larger than those in a solution but smaller than those in a suspension. Two key differences. In a colloid and a solution, particle size is larger in the colloid. There's a specific number for that. And colloids disperse light. So you may see colloids appearing opaque as opposed to a solution where the effect of the solution doesn't disperse light. Colloids also have the impact of Brownian motion. So an example of a colloid is smoke in air, smoke particles in air. Colloids don't settle, however. That's a suspension. A suspension can settle. Colloids don't settle. So a colloid is like that in between us. It's not really a solution, but it's not a suspension. So two popular colloids would be like solid particles dispersed in gas, smoke. Another real popular one that some of you may use nearly every day is an emulsion. And an example of emulsion is milk or mayonnaise or hand cream. If you leave your hand cream bottle down, once it's a good brand you buy, it will never separate into different layers. It's a colloid. It's a mixture. It's not quite a solution. Colloid. Gels, gelatin, that's also a colloid. So suspensions are easy. Suspension is a heterogeneous mixture in which minute visible particles of one substance are dispersed in another substance, and the other substance is usually a liquid. Suspensions are when the particles are huge. Most of the times you see it with your naked eye, and if you leave it, it will settle under the effect of gravity. Popular examples will be dust in air. Dust settle on the table, and your mother will tell you clean the dust off the table. Dust settle on your chemistry book, and your mother will tell you, nah, dust isn't settling on your chem book, right? Muddy water, the juice, certain particles are suspended in the juice. Not the sugar that's a solution, but certain things suspended in the juice. And when you leave it, you get the dregs. And a really popular one from the lab, liquid, is oil and water. Oil and water, if you shake it, you'll see it kind of trying a thing, but then you leave it under gravity, it'll settle into two layers. Imagine if you had 100 grams of a solvent, like we say water, and you try to dissolve some salt in that. After adding salt, and you reach a certain amount, no further salt will be able to dissolve into the water. It will be saturated. That's solubility. The amount of a solute that will saturate 100 grams of a solvent at a given temperature. Obviously, if you raise the temperature of the water, it becomes easier to dissolve the salt. That's why it's easier to dissolve sugar in your hot tea than in your cold juice. You know that. And here's something strange. If we have the hot salt water where it's fully saturated and we cool it, as we cool it, the water will say, well, we're going back down in temperature. We can't keep so much oil dissolved in it. And we'll start to throw out some salt. Some salt wouldn't be able to remain dissolved. So anyhow, if we plot all these solubility points for different temperatures, we'll create something called the solubility curve, and it looks something like this. And they could ask you all kind of simple questions off of this graph, like how much of a solute will dissolve at a certain temperature, or how much extra can be dissolved if you raise the temperature, and simple questions like that, right? Let's move along to separating mixtures, many different methods. If we have something suspended, we can use filtration. Let's see this diagram of filtration here. And in filtration, we'll be getting the suspended solid out of the liquid with the use of that filter paper. The filter paper is our filtering element that has holes which are big enough to let the liquid pass through, but not the solid. Important words, the thing that is left back is called a residue. The thing that goes into the container is called a filtrate. And sometimes you want the residue, like, I don't know, if you're mining for gold or something, you might want the residue. And sometimes you want the filtrate, like the first step in the filtration process, water, or I don't know, your filters outside your house or something, you want the water, you don't want the dirt. In evaporation, when you're using it for separating purposes, we sometimes help it along by giving it a little heat tuner, something like this. Solvent evaporates away and it leaves the solid solute behind. Now, in this case, the boiling point of the solvent must be lower than the boiling point of the solute, or the boiler with the thing you want. Crystallization part is when we don't carry out the evaporation to the full extent and we leave some of the, what we call this, water of crystallization. Because of the water of crystallization, regular shaped crystals, and this is an experiment that we do, evaporating salt water, sugars, that kind of thing. So take a look at the evaporation diagram, take a look at your crystallization diagram, and memorize off the key points. More separation, simple distillation, fractional distillation. Simple distillation is used to separate liquid solvent from a solid solute, as in the case of if you had seawater and you wanted to get pure water or distilled water out of the seawater, you would use simple distillation. It doesn't need to be liquid solid, it could be liquid, but once both of them have different boiling points, more volatile just means lower boiling point in terms of liquid. The more volatile liquid will boil off first, check our diagram there,
and we'll be able to collect that first. From the time that thermometer starts to go past the boiling point of the liquid that we are collecting, stop collecting, it's contaminated. Fractional distillation, a little extra is added to the process, and this one is more used to separate miscible liquids, sometimes more than two. In most industrial processes, more than two miscible liquids. And it's the same idea. The more volatile liquid will be boiled off first, but there's going to be condensation, and then it's going to boil again. Condensation, boil, condensation, boil. So in the lab, we use beads. In industrial processes, they may use caps. The beads provide the surface for the condensation to occur, and then evaporation and boiling can reoccur, with the more volatile liquid being able to go up, turn into a vapor again, and the liquid that's less volatile may just turn back into liquid and drop back down the fractionating column. So we will be getting at the very top only the most volatile liquid first. The most volatile component will be extracted first, and it will be maintaining that temperature. And as the temperature starts to rise, we need to switch our flask, because the distillate that we are collecting will begin to have another one of the components in it, and it will maintain the next temperature, and we get that component, and then we get the next component, and you get the idea. So watch the diagram, take note of the key parts: the fractionating column, that thermometer at the top, the LIEBIG condenser. My main is maths, so I don't know the pronunciation to some of these things, I just know how to spell it. That's where we have liquid going in and out to condense the gas that we collect at the top back to liquid again. That's a condensing chamber where we have water going in and out, and the water is sometimes held at a lower temperature so that it can condense the vapors that escape at the top and send it back to a liquid. We collect that as our first distillate, second, third, how many components we have. So just before we jump on from this, I think the key point is that the more volatile component goes up the fractionating column and is distilled first. When the liquids are immiscible and they don't mix oil and water, classic example, we can use a separating funnel, let them settle, open our tap, collect the more dense liquid. As soon as it starts to see it reaching close to the thing, close the tap, pour that mixture layer, the little boundary layer now. Close back the tap, bring it back and collect your oil on top. The mixture layer, that's the waste, but we'll mostly get water in the first container and we'll mostly get oil in the next container. Alright, there's also paper chromatography. This is more used to separate dyes. This is more used in testing. It's not like you're going and collect the thing that you separate in a big way. And two things it depends on with paper chromatography: how much the component is attracted to the paper and how soluble it is. So if it's more soluble and less attracted to the paper, it goes further up. If it's less soluble and more attracted to the paper, then it will stay near the bottom of the chromatogram. Feel like I never used that word in my life, boy. So this creates a kind of spectrum looking pattern, especially if the dyes are colored, if the components are colored, where you'll see the most soluble at the top, and you'll be able to separate it into its components, and the least soluble at the bottom of the chromatogram.